I'll demonstrate how to connect MATLAB to STK13, extract satellite trajectory data from an astrogator scenario, and visualize the orbit in MATLAB using lie plots and Cartesian position data. In this scenario, we're going to be attempting an inclination or plane change transfer. Let's see. To start with, I'll explain how to do a plane change transfer in SDK. The very first thing you'll need is the delta V and azimuth necessary for the plane change to occur. In this case, you can look on the screen in front of me, in front of you, I mean, and read from my MATLAB how to perceive it. The altitude in this case is up to you to change. Altitude is simply however many kilometers above Earth's surface you need. Then you'll also want to input your desired inclination and your starting inclination. Here you can see our desired is 57 and our starting is 28. Then using that, as well as all the values you can see here, you can calculate the delta V, or the velocity, or the delta velocity you'll need to change from one inclination to the other, as well as the azimuth you'll need to angle your satellite at so that the plane change functions correctly. Is done, your second goal will be to open SDK and start a new scenario wherein you added a satellite, and then name either whatever you wish. Just make sure you know what they are called. Then once everything is open and you can see Earth and you have your satellite, you'll right click on your satellite, go to properties, and then go up to here with propagator and switch it to astrogator. Then once you're on astrogator, you'll want to make sure you're on your initial state. You'll set your semi-major axis to what we calculated before. Oh, first you'll set your coordinate type to Keplerian. Then you'll come down here, set it to oscillating, set the semi-major axis as whatever axis you're using, your eccentricity to whatever you're using, in this case 0, your inclination, which is your starting inclination, and then the right ascension of the ascending node, your argument of axis, and true anomaly should all be 0 degrees. Then once all that information is set, you'll come over here to the left, click on the propagate maneuver, which should already be there. Come here, click on the new button, select ascending node. Then once ascending node is here, you'll click on for it. And then if you have anything else in here, you'll click on it and then hit this X button to delete it. And then you don't need to change anything else. Once that's done, you'll come over here, click insert segment after, where you'll add a maneuver, as you can see right here. Then once you're on that maneuver, you'll come down here, you'll change from along velocity vector to thrust vector. You'll type in your azimuth, your elevation, and your magnitude, which is the delta V we found. And if you want to do it in kilometers per second, you can come here, click kilometer, and click second, and it'll auto adjust. Then once that's done, you'll hit insert segment after once more, insert another propagation, and repeat the process from before with the inserting the ascending node and removing the time stop from beforehand. Then once all that's done, you'll come up here, hit run entire mission control sequence. It'll load. Then you'll see on your Earth orbit, you'll see your original, which I've highlighted in green, and the new one, which I've highlighted in red. You can change this by coming over here, right-clicking on your option, and going down to properties and changing the color to whatever is here. Done. We're going to go back to MATLAB, and we're going to switch over to the code I've written to actually run the MATLAB connection to SDK and to process the inclination that we just did. Here you can see that we have this is just to remove any previous data. Then we set our what name we're expecting. In this case, from before it was named April 16, and then the name of the specific satellite we're looking at, which is satellite 1. Then here you can see two separate time variables. The history step seconds allow for full history data steps, and the live pause secs give the pause between live frames in MATLAB. This allows us to see the animation speed and the time step used for the sampling data. Then it would print, connecting to SDK to show that it's trying. Then below here, you can see this UI app ActX get running server, which is trying to connect to SDK 13. Here, it'll catch if it has an error, but otherwise, it'll end and then set UI app visible to 1 if it's working. And then it'll apply this root code here, which gives MATLAB access to the whole SDK scenario. Then this scenario right here, where you can see SC root current scenario, checks whether the scenario exists and verifies the name that we input before. If it's empty, as in it reads nothing, then we'll get this error. And then here you can see if we have a different name, but it is open, it'll give you an error. But if it still works, it'll run anyway. And then the same process is repeated, but with the satellite. However, for this one, we'll need the exact name, so it'll instead print to check the exact name in the browser. And then once we're attached, it'll print that. Then here, under scenario time and EPSec, you can see multiple different sets of code. Each of these allow for the format of STK to be switched to EPSecs or elapsed seconds, which allows MATLAB to run it much easier because all the times go from formatted date strings to simply numerical values. And then below that, you can see where these values define the interval over which MATLAB orbits or requests orbital data from the SDK, and then it'll print the start and stop time of the simulation. Then, under Cartesian position, it'll start checking where to find all of the Cartesian data it'll need to start graphing. This makes the script more portable between different STK setups, like in the next video I'm producing, which will be over the Hohmann transfer rather than a plane change. Then here you can see this cart DP set and this res cart, which retrieves the time, x position, y position, and z position, which you can see through the time vowels and the x, y, z vowels down here. And then it'll tell you it pulled however many Cartesian samples it found. Then it begins plotting. Here I've made 3 plots. One, this first section here, this orbit plot, or the full orbit from SDK data plot, is done so that we have improved visualization and preserve the correct orbital geometry from the SDK. It'll also let us to compare with the final one to make sure no input data is flawed. Then the second one here graphs the approximate altitude over time. This helps prevent an LLA provider crash by computing altitude from radius rather than allowing the system to go on its own. And then last but not least, we have the live MATLAB plot, which satisfies the requirements we had, where it'll plot on demand live. And then further down, here is the code I was using, where you can see multiple graphing sections. Here you can see where I would print the DV we found, which will also check the DV we utilized to make sure they match. And then below that is the local functions I utilized, which aren't too important to explain because they've been covered in the rest of the system. And then now I will run the system, Not for the full time because that'll take around about 5 minutes. But here you can see it beginning to run. You can see it's printed the name of the system. You can see it's connecting to the SDK. You can see it's connected to the scenario. I cut out a little bit of time while it was waiting. But over on left here, you can see the scenario start time and the stop time, the Cartesian group, the full history it pulled, the dataset names, the time, the XYZ, the match dataset, all the samples we're using, and then here you can see it's beginning to plot. It's in this first section, it's just plotting the initial orbit. You can cut this out if you want by instead of going at the ascending node, going at the descending node, and then it'll only run about half of the system, where it'll go over here and then do the plane change. However, I think it works. I think it's best visualized if allowed to do the whole system. Then right there, you can see the plane change occurred, where we applied the DV, and now you can see the altered orbit. Since this system shows the orbit as seen from the North Pole, it'll appear that the change in inclination has become a lot thinner due to it rotating at a higher altitude or longitude or latitude in this case. You can see it's going around again, and then it'll stop once it hits the ascending node once more. And then it'll print that the live plot is complete, and then it'll print the expected handshake values. Then I'll show you here's the approximate altitude versus time, where it drops a little, and then rises, and then drops again. This is as it goes around the orbit. And then lastly, here's the full orbit from the SDK data, where you can see this original plot is our original rotation, and this more oval shaped one is the one with the higher inclination of 57 degrees.